All right, so let's take a look at this 4.2. We're going to start with exponential functions. This whole chapter is on exponentials and logs. Today it's exponentials. And when you think of this term exponentials, it's not like taking something and squaring it or cubing it. Really, an exponential function is something where you're taking a number and it's being raised to the x power. So yeah, x could be a 2, x could be a 3, could be squaring it or cubing it, but in general, for the to look like a function, that's where the variable is. The variable is up there in your exponent. So let's take this exponential function that we've given, and the base, we call this the base of 2, is being raised to the x power. And let's just start with something very basic. And could we just evaluate that function for different values? We're going to go ahead and round to 2 decimal places when we do this. This is a calculator thing. Well, originally it's not, but you can see by the numbers as these progress, it's going to turn into a calculator thing. So this first one, it wants us to find f of -1. So that's going to be a 2 to the -1 power. I'm just putting my -1 in for x. Now remember that anytime you take something to the negative power, that shifts it to the denominator. And so that's going to be a 2 that gets shifted to the denominator. So this would equal 1/2. All right, if I put in a 3, well, that would be 2 to the 3rd power now. 2 to the 3rd power is 8. All right, now it's going to get a little fancier. Next one is going to be a 2 to the 5/2 power. Now I'm going to make you think about this one a little bit. This is not a calculator yet, but this is a good review from literally the first week that we had this course. And you have to remember that the denominator, when you take something to a fractional exponent, the denominator is the root, the numerator is the power. So ultimately, this is a square root of 2 to the 5th power. 2 to the 5th power is 32. Now, this actually will break down, though, so you would, of course, want to reduce that. That'll break down to a square root of 16 and a square root of 2. So that's 4 root 2. Simplified. Okay, now the next one, this will be a calculator problem. So all you're going to do is, if you don't have your calculator, take a second, pause the video, go get it. But what we're going to be doing is just taking it, and it's going to be a 2, and then use your caret, that up arrow that's right above your division key, and just raise it to the 4.92 power. And rounded to 2 decimal places would be a 30.27. Okay, now it does say rounded 2 decimal places. I didn't do that here. I went ahead and left that exact because I wanted to review the radical stuff. But in your homework, of course, pay attention to the directions. They may want that exact. They may want that as a decimal. Okay, let's look at this next one. It says the exponential function f of x equals, and now you can see this gets way fancier this time. You have this leading coefficient out here. Here's the base being raised to the x power. All right, so this function models the average amount spent in dollars at a shopping mall after X hours. What is the average amount spent after 4 hours? All right, a little fancier for sure, but all I'm going to do is be typing in my calculator 42.2, and then I'm going to go ahead and do the parenthesis 1.56, and I'm going to raise that. I'll do the caret, and I'll raise it to the 4th power because it tells me I'm going to spend 4 hours there. All right, now you can do it left to right. Your calculator will keep track of that order. It's going to just be the order of operations. And typing that all in, I get 249 point, and I'm going to round to 2 decimal places, especially since we're talking money here. I'm going to go 93. So the average amount of money spent. So if you spent the 4 hours at the mall, are you going to spend about $250? I don't know, maybe, unless you're just walking around. That would be our answer. Okay, so let's look at solving equations. Now, those were just evaluating. I'm just plugging a number in. Now we're going to look at an equation where I'm actually going to solve. Now, one method for solving exponentials is to get the bases to be the same. I like to call this a one-to-one, and we actually do call it a one-to-one, but it's a different one-to-one than what we were talking about yesterday. So what I'm trying to do is get these bases to be the same. Like at this, if you have 7 to the third and saying that that equals 7 to the x power, well, what do you think x is going to have to equal in order for these two sides to be equal to one another? Well, it's going to have to equal 3. It's the only way it makes sense. So if you can get these two bases to be the same, then you can ignore the bases and just look at their exponents and just make sure their exponents are equal to each other as well. Now, it's going to be way fancier than that. Look at this first example. I've got A. All right, so my goal is to get the bases to be the same whole number value. So I don't want the bases to both be fractions. I want them to both be whole numbers. So when I look at this 1/3 and this 81, I'm trying to think of a whole number that I could write these both as powers. And so when I'm looking at this, what jumps out at me is 3. Now, it does help if you know some of your powers, if you need to maybe refresh your memory on some of that. But I know that 3 squared is 9, 3 to the third is 27, and 3 to the fourth is 81. So I'm going to rewrite this 81 as a 3 to the fourth power. And I'm going to do the same thing with this 1/3. I'm going to write it as 3 to a power. Now, 1/3 is really a 3 to the -1 power. But I still have this to the x. I'll go ahead on this first one and kind of write it like this. So you can see that this ultimately represents the 1/3 being raised to the x power. But a power raised to another power, you just multiply those. So this is really a 3 to the -x equals a 3 to the fourth. Now I've managed to get the bases to be the same now. So I'm going to do what I did up here. If the bases are the same, then the exponents will have to be the same. So I forget about the 3, and I just grab this right here and say, all right, -x is going to have to equal 4, which means x is going to equal -4. That's our solving process. Okay, let's go ahead and go to the next one. On B, you've currently got one that has a base of 2, and then you have the right side, it has a base of 4. I could write these both, and it does, remember, the same whole number value, but you do want to use the smallest whole number value. I don't want to write this as a 4 to a power. I want to write it as a 2 to a power. I want the smaller number there. So I'm going to leave this 2 as is. And this 4 that I see, I'm going to change that 4 to a 2 squared raised to the 2x power. Then I'm going to do the same thing I did last time. Power to a power, that's just going to multiply. So that's 2 to the 4x. This side I don't have to do anything with. And what I've got now are the same bases. So let's grab those exponents. Let's set them equal. X minus 4 is going to equal 4x. Subtract the x. And then divide by 3 on both sides. So x is equal to -4/3. Okay, one more. Let's practice one more time. Looking at these two exponentials, what do you think these could both be written? What base would I want both of them to have? Okay, I'm going with 3. This one's already done, and I know that 27 is a power of 3. This one is going to just stay the same. 27 is really 3 cubed to the x minus 1. All right. This is going to be 3 to the 2x equals multiply, which means I'm going to have to distribute that 3 through this parentheses here. So that's going to become a 3x minus 3. You've got it simplified to the common base. Now grab those exponents. So 2x is equal to 3x minus 3. I'm going to subtract the 3x. So x is equal to 3. Now you can always go back and check if you wanted to. This might be a quick, easy one that we could check with. You could take that 3 and plug it in for this x and plug it in for this x. And what I would end up with on this one is 3 to the 6th power. And on the right side, I'd have a 27 raised to the 3 minus 1, which is squared. All right, I don't know that off the top of my head, but I can check it. 3 to the 6th is 729. 27 squared is 729. So I like my answer of 3 for that because it did check. Let's talk about some places where we see exponentials in formulas. And one of the most common ones that we deal with is interest and dealing with money. And you can see right here, this is a formula you've likely seen before, but it is for compound interest. So when you put your money into like a savings account, well, the bank is going to pay you interest on that because ultimately they're borrowing your money for a while. And so they're going to pay you an interest amount. And what they'll do is they'll like wait a certain amount of time and then they'll say, all right, at this point, we owe you $5 in interest. And so compounding it means that they're going to take that $5 and add it to your account. So let's say you used to have $100 that you were earning interest on. Now you have $105 that you're earning interest on. So every time they compound it, they add to your balance, and that is helping you out because now you're earning more interest because your balance is higher. So the more often they compound it, the better off you are. So let's talk about what all these variables mean in this big long formula. So A, this is going to be the ending amount that you have in your bank account after it's been compounded for a certain amount of time. All right, P, this is the principal. That's a banking term. The principal is your initial investment. So that's that $100 you put in initially. All right, then you always have a 1 plus R. This is your interest rate written as a decimal. Now the interest rate is always going to be an annual interest rate. They always advertise it, oh, it's a 4.5 APR. APR is an annual percentage rate. And so you'll always put that right here, but you'll change it to a decimal instead of a percent. All right. N is going to be the number of times compounded per year. Since this is an annual, like a 4.5, well, they're not giving you 4.5% every month or every day. They're giving it to you every year. So you have to figure out how often they're going to compound it, and you'll divide it by that. So if they're compounding monthly, you'll divide that rate by 12, and ultimately you're getting the monthly rate at that point. Okay, up here, this is basically how many times are they going to be compounding it? Well, they're doing it n times a year for t years. So if you left it in there 5 years and they were doing it monthly, then that would be 12 times 5. That's 60 times they're going to compound it. Okay, so this is one formula, very common. We use that a bunch. But there is also the reality that that whole process of compounding interest doesn't really take some guy in the back room with a calculator compounding your interest. It is just all done by computer. So really, it could be done instantaneously. And so that's what this formula is for. This is called continuously compounded interest. And what this formula is really derived from this formula with just making n get bigger and bigger and bigger and bigger. So not 12, not doing it monthly, not 365, not doing it daily, doing it like every second. And what happens is as this number gets bigger and this number gets bigger, it kind of merges into this formula here. You've probably seen this one too. We call it PERT. P is still that initial investment. E is just a number. We'll talk more about E later on. And then R is your interest rate, always as a decimal. T is the time in years that you're leaving it in there. So let's talk about that number E before we jump in and use the formula so that you understand what the heck that means. So this is what I just got done saying. The more often it's compounded, the more interest will be earned, but there is a limit on that no matter how often it's compounded. And so the larger numbers that we put in for N, right here and here, it gets closer and closer and closer to this value right here. And that value right there is that limit, that's what it's approaching, gets closer and closer to this. And that has a name, that is E. And you have that button on your calculator. You actually have it in two places. The one that we're going to use is the one that's next to your 4 key on your calculator, but it is second. There's like a little LN there. So you're going to do second LN, and that's going to be an E to the X. Because when we use E, we're always using it in an exponential. So you'll always want to have that. You'll type that button, and then you'll be able to put something in for that X value there. Let's practice a little bit. So let's say you decide to invest $8,000 in an account. It pays 7% per year, and it's compounded monthly. How much will you have in 6 years? Okay, let's run it through this formula. So the question is, how much will you have? So we are solving for A. A is the ending amount. And then it's P, the principal, which is your initial investment. That was 8,000. And then in parentheses, it's 1 plus the annual interest rate. That was 7%. We put it in as 0.07. Remember, move your decimal 2 places to the left. Divided by how many times it's going to get compounded in a year. And since they said monthly, then it's going to get compounded 12 times. Close it up. Raise it to the power of N, which is that 12, times T, which is 6 years. And I'm just going to type this in my calculator. Well, tell you what, I'm going to you do what you want to do with this. You could do what we did earlier. You could just type this in left to right in your calculator. But you do got to be a little bit careful with parentheses because you got so much stuff going on here. So it wouldn't be terrible to do maybe a little bit of it. Like I'm going to try doing it, just sort of thinking of it inner to outer kind of thing. I'm going to start with this division. I'm going to do inside parentheses. I'm going to do this division. So I'm typing in my calculator 0.07. And I'm dividing it by the 12. And then I press enter. Then I'm going to add that 1 to it and press enter. And then the order of operations says I have to do this power before this multiplication. So I'm going to raise it to the, not terrible to do some mental math. What's 12 times 6? 72. So I'm going to raise that to the 72nd power. And now I'm going to take it times 8,000. So whichever way you do it, you should end up at $12,160.84. If you're dealing with money, we always round to 2 decimal places. Okay, now how much did you actually earn over the 6-year period? Well, if you think about it, this $12,000 that you have isn't really your money. It's the money the bank gave you for borrowing your money. So, because you only had 8,000. So how much did you actually earn? Well, that's really the 12,160.84 minus the $8,000 that you put in. So that's just $4,160.84. That's what you earned in interest for the 6 years. Okay, let's look at what would change if we compounded this continuously. How much would we have in 6 years if we did that instead of the monthly thing? Okay, this is the PERT formula. So P-E raised to the R-T. Okay, so looking for the amount, the principal is still 8,000. E raised to the 0.07 times 6. All right, this one I'll just do left to right. It's pretty basic, so I'm just going to do 8,000. If you do it left to right, though, you just can't hit enter in between steps generally because sometimes you're messing up your order of operations. So I'm just going to do 8,000 times, and then I'm going to do that second ln. It gives me the e already raised to the power where I can take 0.07 times 6 all up there in that power, and I get an answer of 12,175.69. Okay, so I earned about 15 more dollars by doing that. Not groundbreaking money because it's 6 years, so I got an extra $15 in 6 years. All right, not a big deal. But it does make a difference when you're talking big money. And I know 8,000 seems like big money to you, but not to millionaires. So that little bit does make a difference sometimes. All right, let's keep with these formulas and keep trying through some problems. It says Becca must pay a lump sum of $6,000 in 5 years. What amount deposited today at 3.1% compounded annually will grow to $6,000 in 5 years? Okay, so it's like she's saving up for this bill that's coming up. Okay, this looks like it's compound interest, not continuous. So back to the long formula. A equals, well, okay, it's really not even A. It's actually 6,000 because that's what the ending amount needs to be. I already know what the ending amount is. The initial amount that she has at the beginning is what we are looking for, the P. What do we need to put into our account? So I'm solving for P. In parentheses, it's 1 plus the interest rate, 0.031, divided by the number of times compounded each year. Well, it's compounded annually, so that means once, raised to the 1 times 5. So in my calculator, I'm going to go ahead and compute this part over here first, and then I'll end up dividing by it. So this is fancier than it needs to be. This 1 doesn't really need to be there. This 1 doesn't need to be there. I don't even need to do this in my calculator because I know what 1 plus 0.031 is. It's just 1.031. So I'm going to take 1.031 and raise it to the 5th power. And then I'm going to take 6,000 and divide by that. Okay, now I have not said this, but man, I can't say it enough. When we are dealing with exponentials, you will never, ever, ever round off numbers and type them in. Those decimal places make such a big difference with exponentials. So don't divide by 1.164. You divide by that answer and you go grab all 10 digits, whatever, divide by the whole thing. And what I have then is a principal of $5,150.60. All right. Now, that's what I would put in the bank so that I would have the $6,000 in 5 years. So it looks like I would earn about $850 in that 5 years. Okay. If only $5,000 is available to deposit now, what annual interest rate is necessary for the money to increase to $6,000 in 5 years? Okay, well, I already know if I only have 5,000, I don't have this much, so this interest rate better go up. I need a higher interest rate. What interest rate? Okay, so all we're doing is kind of the same formula over and over, but just solving for different values. So here I go. I'm putting in 6,000 for the ending amount again. But this time I know the beginning amount is 5,000. 1 plus whatever rate, I'm trying to figure out the rate, it's still being divided by 1, still 1 to the, or 1 times 5 for your power. Okie doke. So let's clean this up a little bit. This one's probably the trickiest one for the solving. I can't really add these together yet because it's an R. And so I can't really take it to the fifth power, but what I can do is divide by 5,000. So 6,000 divide by 5,000. That comes out really nice for us. It's a 1.2 equals 1 plus R to the fifth power. Okay, now think about that. What would you do next? Well, I need to get rid of that fifth power. So I'm going to fifth root both sides. Okay, to get your fifth root, you get that in your math menu. So you'd hit math and it's number 5, where you get to pick whatever root you want. So I'm going to put a 5 and I'm going to put in a 1.2. So I'm doing the fifth root of 1.2, and I can write 1.04 is what it would round to, equals 1 plus R, but I will not type in my calculator 1.04. I will grab the full value. And what it looks like I need to do is subtract 1. All right, well, I can do that in my head, but really what I'm getting here then, I would have R is equal to, now what I'm seeing here is a 0.03737, but typically they will report your interest rate to 1 or 2 decimal places. So what I would do with this is I would go ahead and move it over 2 places, and I'm going to call it a 3.71% interest rate. So yep, it is bigger than the 3.1 that I had earlier. It's actually a little higher than I would have thought it was going to be, but there it is. All right, so there are a lot of exponential models, and models are kind of like formulas that you use, where E is used as the base. There's so many different applications where we can do that. And so we have sort of a basic formula that we use, and it involves anything with any growth or decay. So it has exponential growth or exponential decay. The amount present at any particular time can be modeled by this right here. It's actually kind of like PERT, to be honest, where this is the ending amount, and this Y sub O here, this, anytime you have a sub number of a 0, that is always the initial amount. So that would have been like your principal, your initial investment. Okay, but it doesn't always have to be about money. And so that's why we're using kind of a different formula. And then E is the base raised to the KT. T is still time. K is just some constant that this particular scenario is representing. I'm not really going to do an example specifically for this. I just want this to look familiar to you when you see kind of a generic formula that's been given to you that has an E in it. Okay, this is our last one. This is going to be using our graphing calculator and seeing, all right, how do you do exponential models with a graphing calculator? So what do we have here? It says the data from a recent years, well, indicate the future amounts of carbon dioxide in the atmosphere may grow. Okay, so sorry, I'm not reading this very well. They've collected some data. They're looking at what is happening. They're seeing the amounts of carbon dioxide in the atmosphere growing, and they have determined that it's going to grow at the rate we're looking at here on this table. Now, the amounts given are parts per million. So ppm means parts per million. So 353 parts per million. So make a scatter plot, determine a good model for the data. All right, so here we go. We haven't used our graphing calculators to make a scatter plot in a minute. So let's go through this. First thing we want to do is go into Stat, Edit. You should be doing this with me. And I'm going to go ahead. I'm going to go ahead and leave the years as is because they haven't indicated otherwise. You know, sometimes we call this year 0, and then the next year you go up by that. I'm going to go ahead and keep the years, I think. So I'm going to go 1990, 2000, 2075, 2001 75, and 2002 75. Put in then in list 2 your Y values. Okay, make a scatter plot. But before you make a scatter plot, we've got to fix something. What do we need to fix? The window. All right, look at your X's. What would be appropriate X's? All right, I'm just going to start at 1900. And I'm going to go to, now typically we try to look at predicting into the future. So I like to give a big window to the future. So I'm going to go to 3000 and hope that that's enough. All right. Now my scale, I'm going to go by 100s. And then for my Y's, I might as well just start at 0 on that and go to 3000, I guess. And then I'm going to scale that by 200. And then I'm going to hit my graph and hope I see, oops, nope, you know what? I don't see a graph. Why don't I see a graph? Because my plot's not turned on. So back to, oh, and you might go to your Y equals and clear out any old stuff you got there. And then go up on top of plot 1 and turn it on. All right, okay, looky there. Now future, or in the past, you might have looked at that and thought that was maybe linear looking. But what I'm going to do, here's what I am looking at. I can kind of see these are pretty close, and then, but there's kind of this curve sort of happening. And that is a classic exponential. Looks like this. That's what exponential functions do. They kind of start off slow and then they shoot off and go up very rapidly. So it says determine a good model for the data. All right, this is new here. A model means a regression. So let's go to stat, calculate, and we've done linear, we've done quadratic. I need you to go down to, go down, down, down. Oh, there it is. At 0 is an exponential regression. That's what I want to run, is an exponential regression. So hit that. Don't forget, we skip over frequency list, and on the store regression, we go to vars, yvars, function, y1. Then calculate it. It's going to calculate it so that I could write it. So I'm going to write my model right here. Y equals, the A value is 0.0019. I'm going to go there. I hate to cut it off because I know I'm going to need those decimals, but that is why it's automatically going into our Y equals. All right, my B value, 1.006. Again, I'm going to round it off to that, but I have the full value in Y equals right now. If you go look, I've got all the numbers there. It says use your model to determine when it will reach a level that doubles the initial amount. All right, now doubles the initial amount. What do you think that means? How much will that be? Well, they're talking about this initial amount. We want to double the initial amount. So that means instead of having 353, I want to have, if I double that, that'd be 706. So I want to know in what year will it be 706? Okay, well, I know that it's going to happen in this range right here, but that's a big range. So this is not linear. It's not going to happen like right in the middle or something. So you've got to trust the model. Now, since I know the Y value, that's the trickier version. When you know the Y, that's when you have to go into Y2 and you put in what you're shooting for. So again, double the initial amount would be 706. So I'm going to put 706 in there, and then I'm going to graph it. And it's graphing my exponential. It's graphing my horizontal line at 706, and I'm going to go find that intersection. So second trace, intersect, I just do enter, enter, enter. And there it is. I am getting when when y is 706, the x is going to be 2103.98 is really what it would be. Now, remember what this means. We've talked about this. This is the year. So I really don't want the 0.98 in there. This is the actual year that it's going to happen. Do I round it up? Nope. The 0.98 just means it's happening way, way, way late, like December 30th or something in the year 2003, 2103. So it's a year. Don't give me decimals on that. Okay, that's all I've got. We've done lots of different types. Hopefully this helps you on your homework. Good luck.